Hello, everybody. This is Professor Ma, and this is the sections on derivatives and graphs. We are going to look at the pictures and its relationships to derivatives. So, when we say the derivative and it exists at a point over here, we have a functions defined on a open interval, and the idea about the open interval is that x is a point in the open interval. The reason we have open interval is that we don't want to put the x at endpoints. Okay. And that's a different story. So, but in general, so it's just some x in the middle, and we say the derivative exists means that if I draw a series of lines connecting to its neighbor to the right-hand side, and the line will begin to slowly form. And also, if I do on the left-hand side, and from the two sides, they're going to converge to a one single line, which is a tangent line. Okay. And in particular, that if the derivative doesn't exist, means it coming from the right and coming from the left, I will obtain two different tangent lines. Suppose the derivative exists coming from the left, coming from the right. So it forms a corner there. So the geometry is that if the derivative exists at a point, then the graphs is going to be smooth around the neighborhood left and right to that point. And over here, when we say again that the derivative exists, it means it exists around a neighborhood on the right and on the left hand side. Okay. In particular, if we have derivative equal to 0, that's the tangent line is flat. Then we have the following four cases. We can have they form the top and bottom of the curve where things are flat, or they could form these halfway flat points. So all these we call the derivative at these points, derivative 0 equal to 0, we call these points flat points in these power points. Okay. And how about points where the derivative is positive? Well, the derivative is the slope of the tangent. So if the tangent is positive, all I have to do is take all these curves and rotate them and a little bit of positive slopes, and I get these four possible curves around a point where which derivative is positive. Mind you again, these are the only possible shapes the way it twists and bends if the derivative is positive at that point. Okay. Similarly, you can think how to draw the derivatives if it's negative, have all the tangent line pointing. So suppose I'm given a curve that's differentiable smooth everywhere from one end to the others, and let's just identify some important points we call critical points. Okay. Those are where the derivative is equal to 0. Okay, so in particular, the highest point we call that a maximum. In this case, it's the highest points across the whole domain, so it's the absolute maximum. You can have infinitely many absolute maximum, like the sine of x, and so notice if it's the idea of the absolute maximum or minimum. The idea of absolute maximum, it really depends on how the domain is. And from here, C is the highest point. But if this is part of a bigger functions, then it could be somewhere else is higher. So it's not absolute x maximum anymore. In that case, we call this a local maximum. Okay, so so the idea of absolute and local max, on minimum, really depends on the range you're working in. part of the curve, of course. Okay. And similarly, you have this definition for minimal, and I will let you read it. Okay. And but the point about this is the absolute maximum, absolute minimum for differentiable functions. The derivative at those points must be 0. And however, you can see in the pictures, there are points where the derivative are 0, but they're not maximal nor minimal. Okay. We'll get to that shortly. And in particular, where derivative is positive, remember where we have those 4 pictures, and that's where we say the derivative is increasing. And why we say increasing? Because that means if I go from, if I have 2 inputs, U and V, and the bigger inputs, we have bigger outputs. The Y will be bigger. Okay, so on the pictures, it means it gets higher. If I were to view this as the roller coasters, and here's a roller coaster tracks, and the increasing will be the parts you'll be climbing up, going uphill. So we say the formula is non-decreasing if the inequality is not strict. Okay. So similarly, we can define what we mean by decreasing in an open interval. So in this case, the function is going decreasing. That is, in this picture, the function is decreasing from here to here, or x from C to D, or from here to here, D to E. Okay. And similarly, decreasing means the bigger the input, the smaller the output. We're dropping, the output's dropping. So summary, these are the pictures for derivative equal to 0 and derivative is bigger than 0. And if derivative is less than 0, it means go downhills, and I'll leave that for cases for you to draw. Okay. And in particular, for the functions x to a power, we can look at its derivative. If it's even power, then the derivative must be r power. Then the r power, if x is negative, then the r power will give you a negative derivative. So therefore, the formulas, the graph is falling or is going downhill. On the other hand, on the other side, when x is positive, then the derivative is positive. So then on the other side, we get the function start to climb uphill. Okay. And for the function y equal to x to r power, its derivative is to even power. So in this case, if I just take straightforward x third, fifth, and seventh power, the derivative is always positive. So therefore, their graph is always climbing. It's always increasing, except at 0 and 0. It's stationary. Okay, and so let's take a look at how we use this for graphing. And so let's look at the graph of polynomials and now x minus x cubed. And first, let's get sign chart. So this is 9. Take the x out, minus x squared, and factor 3 plus x, 3 minus x. So I get 3 roots, 0, 3, minus 3. And the sign chart is going to be minus plus, minus plus. Okay, I know that. And here's a graph. Now, what can the derivative tell us? Well, derivative, you can take the derivative and set it to be 0, and then it tells us where this derivative tangent horizontal. Okay, and I can solve for them. They are equal to plus or minus root 3, about 1.7, so somewhere over here. little bit more than halfway. They are those are the max and min. Okay. And here is a sign chart with derivatives. With the derivative, notice it's from here to here is downhill. From here to here is downhill because the sign chart for the derivative are negative. And then, of course, the sign chart for the derivative is positive. Therefore, it climbs all the way from here to here. Okay. So that's what we can gain from looking at the sign chart of the derivative, the up and down of the curve. Okay. Excuse me. Now, let's look at a point where the derivative is 0. And also, we're assuming this is the only point where its derivative is 0. And everywhere around the point, the derivative has a sign. It's either positive or negative. Okay. And now we can break down into cases because they classify what type of point we have at these critical points where the derivative is 0. Okay. If this point is a maximum point, then we must be climbing up and going down. Then that means on the left-hand side of the point A, the sign chart or the derivative of the derivative must be negative, positive. Okay. On the right-hand side, blue side, and it going downhill, the derivative must be negative. So plus and minus. Okay. And then similarly, we can, again, we define what the other in terms of minimums and the things we went through, increasing, decreasing, uphill, downhill, maximum, minimum, they all these counter opposites and sort of definitions, okay, mirror image definition, so you understand why you get the others. Okay, so on the sign chart for minimum, the derivative must change from negative, become positive, must means in geometry, it must be going downhill to the valley, minimum, then climb up, become positive. Okay. And then there are two other possibility where the derivative become 0. And that is, it could be, and the derivative is positive on both sides of the point with 0, or both sides are negative. Okay, I call this the shoulder point because you resemble where the flat point and the shoulder is. And nobody else uses this terminology, so I will use it just for this PowerPoint. And you can use it on the test. Okay. Here's an example comparing the difference between the functions we have in part A, and then I throw in an extra squaring and multiply this by x squared times that. So g is x squared times f. Like, what's the difference between the graph? And why do I use an x squared? Oh, because I don't change the sign chart. So if I just look strictly at the sign chart of this formula and that formula, the sign chart looks exactly the same. So these, in some sense, they have the basic shapes. So what differentiates them, of course, will be the derivatives. And so let's take a look at the derivative of g, multiplying by x squared. And take the derivative, set to be 0, and draw the sign chart of the derivatives. The root of these is root 27.5 and negative root 27. Okay, and so positive on both sides, so uphill. So in particular, it has a flat point in the middle, and it climb on both sides. You must be going uphill, and then flattens out, and then continues to go uphill. And let me point out, when I try to draw something that goes uphill to where it's flat, and I have to go uphill to that point, and I couldn't go uphill like that because I have to go uphill. Oops. I have to go uphill in order to have a flat derivatives 0 there, I have to flatten out. Okay, and this is what I'm trying to explain, that derivative is 0 over here, and in order for me to go uphill on both sides, I couldn't go straight in like that. That's no good. What the curve must do is comes in, go uphill, flatten out in order to continue and go on like that. Okay, so that's a difference between the two curves, between if I multiply x squared to g of x. Okay, and it created shoulder points, if you like. Uphill, flat, uphill again. And let's take a look at the graph of x plus sine x. And first of all, notice at the point 0, x plus sine x equal to 0. So it passed through 0, 0. Okay, so the graph passed through 0, 0. And now let's take notice that for x, since sine of x is always fluctuating between 1 and -1. So when the x gets bigger, it becomes 3, 2, 3, 4, 5, 6, the sine of x is not going to change x by much. So from there, you can reason that the sum x plus sine x is always positive. Okay, for x bigger than for x positive. In other words, it keeps going up. It's an increasing function. You will see these, and by taking the derivatives, okay? And the derivative is 1 plus cosine. Cosine is always between -1 and 1. So this is always bigger than or equal to 0. Okay? So it means it's always positive, so it's always going up. And when does it equal to 0? It's equal to 0 at these points. So when I plot these points into x plus sine x, x is pi, sine x is pi, so I get the outcome is pi again. So well, x3 pi, I get 3 pi, so etc., etc. So in other words, I will get at this location minus pi, 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 3 pi, 3 pi, flat points. But at the same time, it's going uphill. Remember, it's going uphill all the way. The derivative is positive everywhere else. Hence, we have these shoulder points. Uphill flattens out like a shoulder points, and it goes over. And briefly, this is where derivative fail to exist. Okay, they are also counted as critical points. So here are some examples, and the one in particular we'll point out over here briefly is this here. In the other cases, we have different tangent. If the slope exists from the right, from the left, where it forms a corner. I can talk about the angle between the tangent lines. And here is a corners where as it comes in, the tangent line actually goes, the slope of the tangent line actually goes to infinity. Okay, and the other side goes to negative infinity as it gets closer and closer. So it forms this very sharp point where if I say, oh, what's the angle between this in this corner, it's a 0 degree corner. Okay, and this we call a cusp, where the derivative approach infinity, one's positive, one's negative. However, if I were to turn half of this around, bend it back downward like this, then they both be positive, and then I will have a smooth curve. But at the point 0, the derivative doesn't exist. Okay, so this is the other type of critical points where the derivative doesn't exist. It might be one of these cases. Okay, so this is summarize the derivatives the graphs. Okay, bye-bye. Have a